Hello and welcome to another tutorial. In this tutorial I'm going to continue the discussion on polynomials, and if you follow the last video, we discussed that how to construct a polynomial, which we defined it as an object, a class in Java, and then we mentioned that degree of the polynomial is an important parameter, and then it cannot be less than 0. It should be an integer number. And then we discussed about the string representation, how to override the toString method, and we decided to have the representation from the highest order to the lowest order, the constant term. And now we are going to continue with the evaluation of the polynomial at a given point. So if you look at the polynomial in its traditional or conventional form, it's a0 plus a1x plus a2x squared all the way to anx to the power of n. Now if we just evaluate it exactly in this way, then basically the last term, the highest power, has n plus 1 multiplications, because raising x to the power of n basically means just multiplying x n times by itself and then multiplied by an. So n plus 1 multiplication, the next term is n multiplications all the way to 1 multiplication, and then the constant term is basically 0 multiplication. So n plus 1 operations, n operations, 3 operations, 2 operations, 3 operations, 1 operation, and 0. Okay, and then we also have to add all these terms, so we have n addition operations. So if you calculate all these operations, it becomes something on the order of n squared. Okay, so just evaluating the polynomial in its conventional form has an order of calculation as n squared, but there is a method called Horner's method, and it's basically the most efficient way of evaluating a polynomial. And quite interestingly, in Horner's method, then we only have n summation and n multiplication, so only 2n operations instead of having n squared, something on the order of n squared. We end up with something on the order of n. So it's a linear, scalability is linear, but for the conventional calculation it's n squared, so it can hugely decrease the amount of operations. Now, what is this Horner method? So Horner's method is based on a very clever way of factorizing, or basically organizing the terms in the polynomial. And the way it works is that you start with the last two terms and factor 1x out. So x an minus 1 plus x an, okay? And then so start with last two terms, factor x out, and then add the other coefficient n minus 2, and then multiply it by x again, and then add the next a coefficient, and all the way to a3 x, add a2 and multiply the whole thing by x, add a1, multiply everything by x, and a0. Now obviously you can immediately see that this kind of organization gives you exactly the same result. So we have a0, a1x, and plus a2x squared, right? And then for the a3 we have x, a3, and all the way to x, all the way to x to the n minus 1, an, and then we have nx that multiply by each other and multiply by an. But the difference is that we are avoiding calculating the power in each term. We're just doing addition and then multiplication. And then therefore the way we are going to evaluate or implement the evaluation of the polynomial at a given point, we're going to use a recursive algorithm based on this kind of factorization or organization. And so we create another sequence called bn, and the bn term, the nth term is basically an, and then in each recursive evaluation for bn, we multiply it by x and add an minus 1. So ban minus 2 is the previous term, ban minus 1 times x plus an minus 2. So all the way to b1x plus b1 x0 plus a. Okay. Now what is the value of p at x0? So obviously if you follow all these, so b terms are basically all these parentheses. So bn, and the whole thing here is b1 times x0 plus a0 b0. Therefore p of x0 becomes b0. So if we construct the this b sequence, b0 becomes the value of the polynomial at the given point. Okay. Now the very interesting thing is that if instead of x I put a polynomial, I can evaluate the composition of functions, right? Composition of polynomials. And that's a very interesting thing. So when we implement the Horner's method, we can also use it to implement the composition. And again, it saves us a lot of raising to powers, because it just works based on the addition and multiplication. All right, let's head to Eclipse and try to implement Horner's method. So to recap on this code, we created the polynomial class. We have degree and coefficients. We construct the polynomial mostly based on an array of coefficients, an array of double numbers, real numbers. But we also implemented a single term, ax to the n. And then we also worked on the string representation. We overrode the toString method. And now we are going to implement Horner's method. Okay, so for the Horner's method, I'm going to write the method public. It's going to evaluate the function. Evaluate, for example, at a point double x0, for example, or at point x. And what we are going to do is we are going to create a value equals 0. Okay. And then this is going to be the result, and then for int I equals degree, I greater than or equal to 0, r minus minus, what we are going to do is we are going to say value equals based on the recursive way of writing this down, we are going to, at each step, we are going to take the value or basically coefs at point I, right, or I minus 1, plus this is an minus 1 plus the value, our result, times coefs at I. Okay, so we start with a degree multiplied by so basically we start at degree minus 1. So value, we start with the value coef at degree. Okay, this is our an, in the beginning, so bn equals an, and then we add in each step we say bi is basically the value is basically the value of the sequence, right? We take the coef I multiplied by x plus the next coefficient. Okay, so bi is a I minus 1 or ai minus 1 plus b, maybe that's ai plus b I plus 1 times x0 or x. So what we are going to, so the mistake that we made here was that at each point we have to multiply by x, and then we just add it, right? This becomes the new value, and then let's go back to the PowerPoint. So we start with the value of an, okay, and then at each step what we do is that we take our value multiplied by x0, the point that we are evaluating, at the next coefficient. Okay, so we should have basically value here, and this works, and then return value. So to test this, we can go here and we have our let's create a simple polynomial. P2 is a new polynomial 0 0 0 1. So this is x cubed, basically x to the power of 3, and then system.out.println P2. Let's print the expression. It's x3, okay, and we are going to say system.out.println P2.evaluate at point 1, for example. So this should return 1. Yes. At point 2, this is going to return 8. And now it's returning 4. The reason is that let's see. So we start with the degree, okay, and at point let's go back to the PowerPoint. We multiplied by x, okay, and then add the degree minus 1. So this should be degree, okay. Now it works. 3, it should return 27, right? Now let's write x3 minus 1, and we end up with at x3 27 minus x3 minus x squared. right? So x3, this is the coefficient of third term, this is the coefficient of the x squared. 27 minus 9, 18, that's right. And x3 minus 1, 26, minus x3 minus x minus 1, 27, 24, 23. Okay, so this is correct, this works. So what did we do here to recap? So we started with the last coefficient, and in each step we multiplied the coefficient by the current value and added the previous coefficient, and we just repeated this basically n times. Okay, and then this basically implements the Horner's method. And to mention again, this is the most efficient way of evaluating a polynomial, and this is the order, or capital O of n. So it's a linear, the scaling is linear instead of n squared. If you just wanted to use the power or the multiplication for each term separately and then add the results, you end up with the order of n squared. All right. Now the other thing that I mentioned is that we can use exactly the same Horner's method to do composition of polynomials. And composition simply means replace the x by another polynomial, q of x. So public, and it should return a polynomial. Okay, composition, and the input is polynomial q. So how do we implement this? So we take q, instead of having basically x here, we should have the polynomial here. But before implementing that, we have to implement the algebra on the polynomials. Okay, so let's return null for now, and then go back to the PowerPoint, and the algebra, addition, subtraction, it always returns a polynomial. The result is always a polynomial, and the coefficient of the result is term by term coefficient of the p and q, and the degree of the sum or subtraction is the max degree of p and q. Okay, now for it could be that the highest terms are identical, so the degree reduces, but in general, if we want to implement it in a general way, the general principle is that this is like the general case. There are special cases when the terms cancel out, and that therefore the degree reduces, but in general you end up with the max of the degree of p and q. Multiplication, the same way, it always returns a polynomial. The coefficient of each term, first of all, if p is of degree n and q is degree m, the degree of s is pm plus n, so the degree of s, basically degree of p plus degree of q. This is the general case. And then the coefficient of s, you evaluate it based on the convolution of the coefficients of p and q. So you evaluate a convolution sum, and the convolution sum is that there's an running index n minus I times qi, p n minus I times qi, and I goes from 0 to n. So pn multiplies by q0, pn minus 1 multiplies by q1, all the way to pn multiplies by qn. Now division is more complicated because the result may not be a polynomial, there could be a remainder, and therefore the result is not guaranteed to be a polynomial. So we're not going to implement it the same way that we implement the addition, multiplication, or subtraction. The result is something that called a rational expression. Rational is basically a fraction that has a polynomial as the numerator and a polynomial as the denominator. And the theorem of division states that the remainder is a polynomial that has a degree less than q. So the degree must be, this is strictly less than q. It cannot be equal. Okay? And there are ways to calculate this remainder. So the tip here is that we can, because eventually we want to implement the operator overloading for polynomials as well, because these are some sort of functions. And we can implement this algebra as part of the operator overloading. So in order to do that, I'm going to go to Eclipse. I'm going to create a private, basically polynomial, plus polynomial q. So this is p plus q, or this object plus q of x. And what we are going to do is we are going to create a integer n or m, for example, which is math.max of this dot degree and q dot degree. Okay, and then double coefs sum equals new double m. Okay, for int I equals 0, r less than m, I plus plus. What we are going to do is coefs sum of I equals this coefs I plus q dot coefs I, and then return new polynomial. Basically coefs sum. Now the problem here is that maybe the degree of q is less than the degree of our current polynomial, this polynomial. So this could throw basically an exception, because it goes into array out of bound exception. And in order to avoid that, we can write an if. So basically a few ifs. If I is greater than q dot degree, then and I less than or equal to p this dot degree, then this term only belongs to this object. All right. Else, if I greater than this dot degree and I less than or equal to q dot degree, this term belongs to only the q. Q dot coefs I. Okay, and if I is less than the degree of both, then the term belongs to both of them. Okay, now I'm going to make it public, and okay, let's keep it private, and then go and do operator overloading. So operator overloading, operator overloading, and in the operator overloading I'm going to write public polynomial. And what happens if we private polynomial plus, but this time we have a, so this dot double coefs sum new double degree. Okay, the degree doesn't change, and then basically for int I equals 0, I less than degree less than or equal to degree I plus plus coefs sum I is basically coefs I, but then basically we made a copy, but coefs sum 0 is plus equal v, and then return new polynomial coefs sum. So if it's just a double number, it just adds to the constant term of the polynomial. If it's polynomial, then we have to first figure out what the relation of the degrees are. The degree of the sum in general could be the maximum of the degree of the two polynomials, and then if we are adding term by term, depending on if the degrees are depending of the index of the term is greater than the degree of one of the polynomials, or is less than the degree of both, then we have to figure out how to sum the terms. Okay, add double v, basically return this plus v. Okay, and then public polynomial add reverse double v, return this plus v. Okay, and the same thing here, but here we have polynomial and it still works because we have this. Okay, now let's go here. Polynomial p3 equals p2 plus 2, and system.out.println p3. So we get an array index out of bound exception, and when I is degree, so coefs are okay, degree plus 1. And here also if the degree here, we have to have n plus 1 coefficients, right? Yes. All right, let's test this. So p2 is I'm going to delete this, and then going to write p2 equals plus p2. Remember, when you concatenate a string with an object, the compiler automatically calls the toString method on the object and then append it to the string. and here is p3 equals, or p3 equals p2 plus 2 equals plus p3. X cubed x squared minus x minus 1 x cubed plus x squared minus x plus 1. So it just adds 2 to the constant term, and we also implemented the reverse addition, so this has no problem. So we add 5 to the constant term. All right, so this was adding a constant number to the polynomial. Now we are going to add another polynomial, so adding a polynomial p4, new polynomial, and 0 x 2x2, that's it. So p3 is x cubed, the degree is 3, or p3 is third order, p4 is basically second order, and then polynomial p5 is p3 plus p4. And system.out.println p5. All right, let's see what we get. p3, p4, and p5. p3 is x cubed, x cubed minus x plus 4. p4 is 2x squared plus x plus 0, and then the term by term, so x cubed only appears in p3, so it should directly come into the result. Okay, x cubed, and then we had 0x squared, 0x squared here, 0x squared, 2x squared, so we get 2x squared, minus x plus x, we get 0x, plus 4 plus 0, we get 4. Okay, so the key point in implementing the addition was that you have to set the degree of the result as the maximum of the two, and then create an array of the degree plus 1, okay, for the result, because now we know what the degree of the result is. But then the problem is that the degree of one of the two polynomials, either this polynomial may be less than this degree of the result. Okay, then if we add term by term from the coefs arrays, we might run in the array index out of bound exception. We might end up with that. In order to avoid that, we have to have these two if. Basically, these are test cases, tests to make sure that we are covering if the one term only appears in one of the polynomials, we just use that. If the term appears in both of the polynomials, we just use that. Now, similarly, the same way, we can implement minus. This just becomes minus. Now, because minus means this minus q, if the term only appears in q, we have to use negative here, and then now here negative. And then we go here, add, subtract reverse, subtract reverse, minus 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 minus. Okay, and test here. P2 minus 2, P4, P3 minus P4. I'm going to comment rest out, or maybe just remove them. So P2 is x cubed 0x squared minus x minus 1, and P3 is P2 minus 1. So x cubed is the same, x squared is 0, minus x minus 1 minus 2 is minus 3. Okay, and then we have P4 2x squared plus x plus 0, and then P3 minus P4 x cubed 0 x cubed comes down, 0x squared minus 2x squared minus 2x squared minus 1x plus 1x equals minus 2x minus 3 plus minus 0 minus 0. Okay, the minus subtraction also works. Now in the next video I'm going to implement multiplication and other additional functionalities, and in the next video we are going to conclude our discussion on polynomials. Thank you for watching. I hope you enjoyed this, and see you in the next video.